Hello and welcome to Weapons of Math Instruction. Thanks for joining me for this week-long celebration of Pi Day. In this video, we're going to look at how the great mathematician Archimedes approximated pi. So in the last video, I gave two geometrical illustrations that show that the number pi sits between 3 and 4. In this video, we're going to tighten up those bounds using Archimedes' method. Archimedes was a Greek mathematician who lived in the 3rd century BC. Needless to say, he didn't have a lot of technology at his disposal, which makes his accomplishment all the greater. So Archimedes approximated pi by considering polygons circumscribed around and inscribed in a circle. You got a taste of circumscribed and inscribed polygons in the last video. You'll see more of that in this one. The perimeters of these polygons give approximations of pi. For the purposes of a derivation that I'm going to do towards the end of the video, I'll introduce some notation. So this function here, PC of n, will denote the perimeter of an n-sided circumscribed polygon. So the subscript c stands for circumscribed, and the argument of the function n is the number of sides of the polygon. And the perimeter of an n-sided inscribed polygon, I'll call that pi of n, where of course the subscript I stands for inscribed. Consider a circle of radius 1/2. So remember, the circumference of a circle is 2 pi r. So if the radius is 1/2, then the circumference is 2 pi times 1/2, which is pi. And what we're going to do is circumscribe a square around the circle, like this. You already saw me do this in the last video, but with a circle of radius 1. So I'm going to draw a line segment from the center of the circle to the upper right corner of the square to complete a 45-45-90 triangle. And since the measures of these two angles are equal, the measures of these two sides are equal. So this is 1/2. In fact, the lengths of the sides of a 45-45-90 triangle satisfy the ratio 1 to 1 to the square root of 2. That's going to be handy when we look at the inscribed square. So this half here is half the length of one side of the square. So the full length is 2 times 1/2, or 1. Which means that the perimeter of the square is 4 times 1, or 4. And here I've used that fancy notation from the previous slide. So again, this denotes the perimeter of the circumscribed polygon of 4 sides, which is of course the square. Okay, so here, let's clean up the circle so we can inscribe a square like so. And I'm going to draw another triangle. So notice I've gotten rid of that original radius because I drew in these two to make this triangle here. So since these two sides of the triangle are both radii, their lengths are both 1/2. And using the ratios of the lengths of a 45-45-90 triangle from the previous slide, we see that the hypotenuse of this triangle has to be the square root of 2 over 2. But that hypotenuse is just the length of one side of the square. And so we can find the perimeter by multiplying the length of that side by 4, and the perimeter is 2 times the square root of 2. So let's gather our results. Here I've drawn our circle with both the circumscribed and inscribed squares. Remember, the circumference of the circle is pi, and we can clearly see that the perimeter of the inscribed square is less than the circumference, and the perimeter of the circumscribed square is greater than the circumference. Plugging in the numbers, we get this inequality here. Now, Archimedes didn't have a calculator, but he did know how to approximate square roots with fractions, and that's what he did. I don't want to get bogged down with his method for finding square roots in this video. That'll be a topic for another video. So we'll chuck that square root into a calculator. And using the circumscribed and inscribed squares, Archimedes found that pi sits between about 2.828 and 4. We can do better by increasing the number of sides of the polygon, and that's what we're going to do. Okay, let's clean up our circle again so we can do more work. This time, we're going to circumscribe a hexagon around the circle and see what we can see. So here, I've made an equilateral triangle by drawing line segments from the center of the circle to 2 adjacent vertices of the hexagon. The third side of the triangle is one of the sides of the hexagon, right here. Notice that these line segments here and here, they go beyond the circle, so they are not radii, and in fact, I don't know yet what their length is. So what I'm going to do is cut that equilateral triangle in half to make this 30-60-90 triangle. So the side opposite the 60-degree angle, that's the radius, 1/2. The side opposite the 30-degree angle has length square root 3 over 6. How do I know that? Because The lengths of the sides of a 30, 60, 90 triangle satisfy the ratio 1 to square root 3 to 2. And using the first two members of the ratio, I see that this has to be the square root of 3 over 6. So this is half the length of one side of the hexagon. So the full length is 2 times that, or square root 3 over 3. And once I know the length of one side of the hexagon, I can get the perimeter by multiplying by 6. So the perimeter of the circumscribed hexagon is 2 times the square root of 3. So here I've cleaned up the circle once more, and I just bet you know where we're going with this next. Yep, you were right. We're going to inscribe a hexagon. You saw me do this in the last video. I'm going to complete an equilateral triangle like so. Now this time, I do know the lengths of all 3 sides. They're all equal to the radius of the circle, 1/2. So this here is one side of the hexagon. Its length is 1/2. And we can get the perimeter by multiplying that by 6. So the perimeter of the inscribed hexagon is 3. So let's collect our results and get a bound on pi. Okay, the circumference of the circle is pi. The perimeter of the inscribed hexagon is less than pi. And the perimeter of the circumscribed hexagon is greater than pi. And let's plug our results in. Pi sits between 3 and 2 times the square root of 3. And again, we'll chuck this square root into a calculator. And what we find is that pi is between 3 and 3.464. So notice, this is an improved bound over the one from the last video, because in the last video, we showed that pi sits between 3 and 4. Already, we've tightened it up by reducing the upper bound. Archimedes continued his approximation for polygons of up to an astonishing 96 sides. I say astonishing because he did all this by hand. But he didn't draw out figures for each polygon. Instead, he stopped with hexagons and then devised ingenious formulas for calculating the perimeters of the circumscribed and inscribed polygons every time the number of sides doubles. I'm going to show you the derivation of these formulas next. I'll warn you now that the derivation is trigonometry heavy. So if you want to stop and skip to the end of the video where I calculate bounds on pi using an Excel spreadsheet, I wouldn't blame you. Hey, you stuck around. I'm proud of you. Let's get our hands good and dirty. In his analysis, Archimedes noticed some trigonometric patterns. Now, he didn't know trigonometry in the familiar form that we know it, with sines, cosines, and tangents. But he did know something equivalent to modern trigonometry, at least enough to be able to solve this problem of approximating pi. So let's start by looking at the perimeter of the circumscribed square, which was 4. Now, this is equal to 4 times the tangent of 45 degrees, because the tangent of 45 degrees is 1. And going a little further, 45 degrees is 180 degrees divided by 4. Here's the perimeter of the circumscribed hexagon. It's 6 times the square root of 3 over 3. And the square root of 3 over 3 is the tangent of 30 degrees. And furthermore, 30 degrees is 180 degrees divided by 6. Now notice, we see a pattern emerging. In both cases, we see the number of sides of the polygon here as the coefficient of the tangent function, and here as the quotient of the angle. The same thing happens here. We get 6 and 6. Archimedes was able to show that this pattern holds in general. So now, he didn't need to draw any more triangles inside of polygons to get the perimeter. Let's look at the inscribed perimeters. So here's the perimeter of the inscribed square. It's 4 times the square root of 2 over 2. And the square root of 2 over 2 is the sine of 45 degrees. And 45 degrees is 180 degrees divided by 4. Here's the perimeter of the inscribed hexagon. It's 6 times 1/2. And 1/2 is equal to the sine of 30 degrees. And 30 degrees is equal to 180 degrees divided by 6. And so again, we have a pattern emerging. Here and here, we see the number of sides of the polygon in both cases, right? And again, Archimedes was able to show that this pattern holds in general. So here we have a formula for the perimeters of the inscribed polygons with n sides. And so this is great. So when Archimedes was solving this problem, he did the perimeters for the squares and then the hexagons, and then he thought, this is for the birds, I gotta speed this up. So what he did was he devised formulas for calculating the perimeters of the circumscribed and inscribed polygons every time the number of sides of the polygon doubles. And he did it using the following facts. This here is the half-angle formula for the sine function, which was known to Archimedes. Also known to Archimedes was the half-angle formula for the tangent function, And lastly, we have the Pythagorean identity for the sine and cosine functions, which he also knew. Now you might be thinking, why the heck do we need formulas for the perimeters when the number of sides doubles? We can take these formulas and plug in any n that we want. And you'd be right. But Archimedes couldn't do that. He didn't have easy ways for calculating tangents and sines of arbitrary angles. So I'm going to show you this derivation just so you get an appreciation for some of the pain that Archimedes went through. Okay, here we go with the derivation. Here's the formula for PC with 2n plugged in for n. Notice that the angle of 180 over n has been cut in half. So, I can use the half-angle formula for the tangent function, which I've done right here. In the next step, I'm going to divide the numerator and denominator by n sine 180 over n. When I do that, the numerator simplifies to 2. Everything here cancels except the 2. And in the denominator, I divide term by term. So here I have 1 divided by n sine 180 over n. That's here. And here I have the cosine of 180 over n divided by n sine 180 over n. That's here. Now, the tangent is equal to the sine over the cosine. So this cosine over sine is a reciprocal tangent. And so this is going to simplify to this, with the tangent in this denominator here. And these two should look familiar. This denominator is pi of n, and this denominator is pc of n. And this is how Archimedes got around not being able to do trigonometry on a calculator. With this formula, he could calculate the perimeter of the circumscribed polygon with 2n sides from his knowledge of these two perimeters of polygons of n sides. Now let's get a formula for pi of 2n in terms of the perimeters of the n-sided polygons. So here we have pi of 2n equals 2n sine 180 over 2n. And again, the angle of 180 over n has been cut in half. And so this time, I'll use the half-angle formula for the sine function, like so. Now in this next step, I'm going to be a little sneaky. Under the radical, I'm going to multiply the numerator and the denominator by the Pythagorean conjugate of the numerator. And this is so that I can use the Pythagorean identity from a couple slides back. When I carry out this multiplication on the top and bottom, in the numerator, I get 1 minus the cosine squared of 180 over n. And in the denominator, I just get these two factors sitting next to each other. Now, 1 minus cosine squared is what you get when you solve the Pythagorean identity for sine squared. And so I can replace this with sine squared, which I do right here. In the next step, I take this 2n outside the radical, and I bring it inside as 4n squared. And now I'm going to split the radicand up into two distinct factors. So I have 2n times this ugly fraction times n sine 180 over n. And this should be recognizable as the right-hand side of the half-angle formula for the tangent function. So I'm going to go ahead and simplify this using that formula. And I do that right here. So here, instead of the fraction, I have the tangent of half the angle. And this just comes over as is. And these should both be recognizable. The first factor, 2n tan 180 over 2n, that's pc of 2n. And this is pi of n. So if you calculate pc of 2n first, using the formula from the previous slide, you can get pi of 2n. So here are the two formulas that Archimedes derived for approximating pi. Let's look at the sample calculation. Archimedes stopped his geometric analysis with hexagons for which n equals 6. And as we already saw, he found PC of 6 is about 3.464, and that pi of 6 is 3, and that puts these bounds on pi. So using the formulas at the top of the screen, we can jump directly to n equals 12, which is 2 times 6. So, according to this formula, PC of 12 is 2 over the reciprocal of pi of 6 plus the reciprocal of PC of 6. And if you work that out, you get about 3.215. And according to this formula, pi of 12 is the square root of PC of 12 times pi of 6. All right, so here's PC of 12, here's pi of 6. If you work that out, you get 3.105. And that puts these bounds on pi. So 3.105 to 3.215. And notice how we're tightening up the interval that pi is trapped in. So increasing n gives us better and better approximations of pi. Archimedes continued this process for n equals 24, 48, and 96. So he doubled the number of sides 3 more times. He doubled the 12 to get 24, doubled the 24 to get 48, doubled the 48 to get 96, and there he stopped. Now, he did all this by hand. We're not going to do that. We're going to turn to an Excel spreadsheet right now. So here I have an Excel spreadsheet. In column A, I have several values of n, and these values double from one row to the next. In row 2, I have our seed values for n equals 6, the hexagons. And then starting in row 3, I programmed in Archimedes formulas. So here's the formula for PC, you can see it there. Here's the formula for Pn, right there. And of course, here's the value of pi for reference. So if I copy and paste these formulas down columns B and C, I could bang out these calculations real quick. And Archimedes would be so jelly if he could see me right now. So down here around row 18, you see that the upper and lower bounds are indistinguishable from each other and from this value up here. So as you can see, this is not a very efficient method for approximating pi, but it's certainly an ingenious one given the time that Archimedes lived in. Okay, thanks for hanging with me through all that. Hope you enjoyed the video, and tune back in tomorrow for another bite of pie. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.